Uh, Hello, everyone. Welcome to the 148th Stanford MedAI Group Extend session. This week, we have with us Gregory Holste from the University of Texas at Austin to talk about his work on AI-enabled echocardiography interpretation. Gregory is a PhD candidate in the Electrical and Computer Engineering Department at UT Austin, an NSF Graduate Research Fellow, and a UT Austin Talbot Enroth Scholar. His research bridges AI and healthcare, developing deep learning methods to solve clinical decision making and medical image analysis problems. Greg collaborates with clinicians to develop AI systems that assist rather than replace physicians by helping them interpret medical images more quickly and accurately. His research has been published in journals such as JAMA Cardiology, Nature Communications, Transactions on Medical Imaging, and Medical Image Analysis. Greg, thank you so much for joining us today. Before you start, do you have any preferences on how you would like to take questions? Uh,
I think what I'll do is I have a few sort of natural stopping points or checkpoints in my talk, and I'll just stop there and field them all at once. But people can ask questions in the chat at any time, and then once I get to one of those stopping points, I'll stop and answer those.
Okay, awesome. With
Okay.
that, let's try to make this session as interactive as possible. Without further ado, let me hand it over to our presenter. Rick, you
All
can
right.
take it from here.
Thank you so much. Let me make
Thank you.
sure my screen sharing works properly. Can you see my full screen? Yep. Okay, perfect. Let me move some things around. Okay. Thank you for the introduction. That's very kind. I've been a fan of this series from afar, so it's very cool to come on here as a speaker now. I work on various applications of deep learning to medical image analysis and interpretation, but I'll be speaking with you all today about my work on AI for echocardiography interpretation. This is cardiac ultrasound. So I want to first zoom out and tell you sort of where I'll start and where we're headed. First, I'll present our work on using deep learning to automatically detect a heart disease called aortic stenosis from echocardiography. We'll then expand the scope of this project to incorporate heterogeneous multi-view imaging and head toward the more ambitious goal of fully automated echocardiogram interpretation beyond just one disease. So this is effectively telling the story of moving from single view, single task modeling to holistic multi-view, multitask modeling that more closely reflects the real-world clinical workflow. But first, aortic stenosis, or AS, is a heart disease characterized by a narrowing of the aortic valve that restricts blood flow. This is a common valvular disease affecting about 5% of the US population over 65. It's also a dangerous one. Once AS progresses to the severe stage, it can lead to serious adverse outcomes like aortic valve replacement, heart failure, even death without proper intervention. Now, the way this is typically diagnosed in practice is through non-invasive imaging, specifically transthoracic echocardiography. This goes by many names, also TTE, also echo for short. These are ultrasound images and videos of the heart captured by a handheld probe from a set of standard views. So sonographers or echocardiographers are trained to capture images from these key views that each have a sort of characteristic appearance designed to assess specific parts of the cardiac anatomy. And the gold standard for assessing the valves of the heart, like the aortic valve, is color Doppler, TTE, which, in addition to the grayscale ultrasound image, also provides this red-blue overlay that also quantifies both the direction toward and away from the transducer and velocity of blood flow. So while color Doppler imaging is part of a complete TTE exam, not all devices are equipped with color Doppler capabilities. And though ultrasound devices are relatively cheap compared to other imaging modalities, scanners with color Doppler are not always available outside of major hospitals and cardiac-focused clinics. So in collaboration with Dr. Rohan Kara, who leads the cardiovascular data science lab at Yale Medicine, our first question was, can we use deep learning techniques to automatically detect AS, this important disease, from echocardiography videos? And critically, can we do it without color Doppler, potentially expanding access to AS screening? So here's a bird's eye view of how we accomplish this. We first extract echocardiographic videos from the Yale New Haven Health System. This is a network of Yale affiliated hospitals and clinics all throughout New England, and then develop a deep learning model to detect severe AS from the parasternal long axis, sometimes it's written out plaques, view of the heart. The model is developed using over 20,000 videos, and we pursue multi-site validation across geography and time to ensure the model generalizes to new patient populations. So after extracting about 15,000 studies acquired during routine clinical practice from 2016 to 2020, we developed software to automatically parse these studies by filtering for the 2D grayscale videos without color Doppler, then automatically removing identifying information like the patient's name that's often burnt into the pixel data, and finally filtering for the desired parasternal long axis view with a pre-trained view classifier. So this resulting data set was then randomly split into a derivation set for model development, an external test set from clinics that were not encountered during training, and a separate temporally distinct test set from 2021, a year later. The modeling approach we take is a two-step process that first consists of self-supervised pre-training, followed by fine-tuning to detect severe AS with deep ensemble learning. But before I get into that, I want to go on a quick detour to better explain this pre-training step by describing a separate study on a method called EchoClear, which we'd previously developed and then used here. So back to our roadmap, I'm going to break down AS detection into two steps. First, I'll cover foundational work on how we actually learn representations of echocardiograms with self-supervised learning. And second, I'll describe how we use this self-supervised pre-training as part of our approach to robustly modeling AS. So first, how do we learn useful representations of echo data? There are many ways to initialize a neural network. You can set the weights randomly. You can draw from your favorite probability distribution. Nowadays, we usually see some form of transfer learning where, the practice of leveraging a pre-trained model is completely standard. Now, in computer vision, as almost all of you are aware, I'm sure, this is usually achieved through ImageNet pre-training, where a model is trained on this large-scale data set to detect 1,000 or more classes, and then adapted to a downstream task by continuing to train the model. And critically, transfer learning is so useful because the target task can involve data from a completely new domain. So while classifying birds and trucks ostensibly tells us nothing about how to interpret an X-ray, it does tell us how to extract visual features like edges, differences in contrast, shape, and color. And those fundamental visual patterns tend to be universally useful, which enables rapid adaptation to new domains. So to summarize, transfer learning separates the training process into two steps. First, pre-training, where the goal is to learn general, transferable representations of data, followed by fine-tuning, where the goal is to transfer that knowledge from pre-training to a new task with the supervision of domain-specific labeled data. Now, while transfer learning typically uses supervised training with external labels, self-supervised learning aims to learn useful representations from the raw data alone. And one of many ways of doing this is contrastive learning. And here I'll highlight one specific contrastive method called SimClear, some of you might be familiar with. This approach uses heavy image augmentation to create two synthetic copies or views of an image to create what we call a positive or contrastive pair. Here, the objective is to learn similar representations of positive pairs, these transformed copies of the same underlying image, and dissimilar representations of copies from different images, negative pairs. This is a very clean, simple idea in principle, but what's amazing is when you pre-train a model this way, it's extremely label efficient, meaning a model pre-trained with SimClear requires far less labeled data than other transfer learning approaches when fine-tuned on some downstream task. So in this table from the original SimClear paper, you can see that a baseline ResNet 50 reached about 48% accuracy when fine-tuned on a small amount of data, just 1% of their labeled data, while an otherwise identical SimClear pre-trained ResNet 50 jumped up to 76% accuracy. As you can imagine, in AI applications like medical imaging, where the bottleneck is often just acquiring sufficient amounts of labeled data, self-supervised learning could be a hugely useful tool to enable learning from small labeled data sets. And indeed, this has proven true, and self-supervised learning has become very popular in AI for medical imaging. But at the time of this research around early 2022, contrastive pre-training methods had only really been applied to modalities like X-ray, CT, and MRI. These have shared properties of high spatial resolution, very standardized acquisition, and ready availability through big benchmark data sets. So this then led to the question, could we adapt a self-supervised learning method like SimClear that was originally developed for natural images to echocardiography videos. Now, the problem with naively applying a method like SimClear to echo is twofold. First, ultrasound images are quite noisy, especially when heavily downsampled for machine learning purposes. As a result, they're quite brittle and sensitive to the heavy image transformations that methods like SimClear rely upon. And second, echoes are spatiotemporal. They're videos with rich temporal information capturing the motion of the beating heart, whereas methods like SimClear were developed for still 2D images. Now, to combat these issues, we developed EchoClear, which performs contrastive learning of parasternal long axis video clips with two key solutions. First, we employ multi-instance sampling, which means we use different parasternal long axis videos of the same patient as positive contrastive pairs. This critically removes the need for image augmentation and forces the model to learn patient-specific phenotypes across different videos of the same patient. And second, we include a frame reordering pretext task where the frames of each video clip are randomly shuffled or permuted, and the model is then trained to predict the correct order of frames. And this encourages the model to be temporally coherent or logically consistent in a way that SimClear cannot. So after pre-training a model on about 30,000 parasternal long-axis echocardiographic videos with EchoClear, this method, we then fine-tune that model to predict severe AS using different amounts of labeled data. For example, 1% of it, then 5%, and so on. All along the way, we compare performance to both a randomly initialized model and a model pre-trained on Kinetics 400. This is a large data set of YouTube clips representing a standard transfer learning approach for videos. So we find that when using 1% of available training data, just 53 training examples, an EchoClear pre-trained model reaches well above zero point 0.8 AUROC, while the standard transfer learning approach barely exceeds random guessing around zero point 0.6. And an ablation study also shows that each component of EchoClear provides additive complementary value. Again, when using small amounts of data, 1 to 5%, SimClear pre-training barely exceeds random guessing. However, when we add multi-instance sampling using different videos of the same patient as positive pairs, this boosts AUROC above zero point 0.7. And finally, including frame reordering on top of this, which gives us the proposed EchoClear boost performance above zero point 0.8. And you can see from these curves that there's eventually a sort of saturation point where once label data becomes abundant, the initialization method doesn't appear to make such a meaningful impact on downstream performance. However, I want to argue that self-supervised pre-training is not just more label efficient in these data scarce settings, but it's also potentially more trustworthy. When analyzing saliency maps of the fine-tuned models using all available data, we see that the EchoClear pre-trained models more closely attend to clinically relevant regions. Keep in mind that these two approaches, represented by the two rows here, are completely identical in architecture. They're trained in the exact same way on the same data to perform the same task. They only differed in how the model weights were first initialized, suggesting the value of pre-training on in-domain data with self-supervised learning. So this study on EchoClear was presented at an ICML workshop and eventually published in Communications Medicine. Now back to our roadmap. I've just covered how we use self-supervised learning to learn representations of echo videos. And now we'll see how we use the insights from the study to reliably detect AS.
Greg, we have a
Yes.
question. Are the videos used for each patient from the same scanning session? I think that's
Hmm.
from slide 8. Yeah, go ahead. Yeah.
I'm glad you stopped here, actually. That was just when I was going to stop for questions. So yes, these videos are from the same exam or the same study. They're also from the same echocardiographic view. They're all from the parasternal long axis view. So we're basically leveraging a fact about the clinical workflow that this is such an important view that often you get multiple video clips from the same view. So we're leveraging those in our contrastive learning method as positive pairs for contrastive learning. And
We
was there
have
another question?
Yeah, there's another question.
Okay.
So it's like you mentioned that the algorithm is mainly intended to be used for a screening.
Hmm.
Is missing AS on echo common?
Oh, I see. I I should say I'm not a trained cardiologist. I don't have this off the top of my head, but um, my understanding is that catching it early before it's severe can be quite difficult. So identifying mild to moderate aortic stenosis can be difficult, and that's when it's most important when intervention can actually have a good effect. Okay, so back to the roadmap. We
We
just
have another
covered.
question. Sorry,
Oh,
we have
yes,
another question. Can you explain more about the contrastive learning details?
sure. Let me go back here. So for contrastive learning, it actually adopts the same info NCE loss function, if you're familiar with that, as the original SimClear paper. The main difference is in how we create those contrastive pairs. So instead of getting one echocardiographic image or video and creating copies by augmenting them, doing transformations to them, we use actually different videos of the same patient from the same exam as the contrastive pairs.
Okay.
I
I
just had a question off of that.
Hmm.
I know in within a study, like if you're acquiring personal long axis, you take it, the general view, then you'll take like a zoomed in version of that.
Yeah.
So I guess my question is when you're creating these positive pairs, do they look very similar? Like I'm just looking at your figure here and they look very similar, but can you create a positive pair, having that like very holistic personal long axis view and then have the positive pair be that zoomed in?
Yeah, that's a great question. So the answer is yes, these can look quite different. Um, exactly like you're saying. Typically, if you're acquiring variations of the parasternal long axis view, one might be more zoomed in. You might focus on a slightly different area. You could change the frame rate even. Um, so yes, these can look quite different, which is what makes it a challenging contrastive learning task. And I think what enables the model to learn these really useful representations that are useful downstream.
Perfect. Thank you.
We have a couple more questions, but I think we
Okay.
can revisit them later on.
Okay.
Yeah.
Sounds good. All right, so now we'll see how we use the insights from this study to help us reliably detect AS. So to identify severe AS on echocardiography, we form an ensemble of three different 3D convolutional neural networks, each with a different weight initialization. And they're actually the same three initializations we used in this earlier study. So one is randomly initialized, another is pre-trained on Kinetics 400, and another is pre-trained with EchoClear on our training set echocardiograms using self-supervised learning. So these three models are then separately fine-tuned to detect the presence of severe AS from parasternal long axis video clips, and their outputs are averaged to form a diverse ensemble. And to further boost generalization, we also employ this hierarchical aggregation scheme where predictions from multiple clips of the same video are averaged to produce a video level prediction. And since there are often multiple parasternal long axis videos per study, those video level predictions are further aggregated to form a single study level prediction of severe AS. So overall, our model detects severe AS with very high accuracy across hospital systems, reaching 0.94 AUC in an external cohort, sorry, in the external New England cohort, 0.98 AUC in the temporally distinct cohort from 2021, and even 0.95 AUC in an external cohort from Cedars-Sinai Hospital in California, generalizing to this patient distribution that it hasn't encountered during training. The bottom row here also shows violin plots of the predicted severe AS probabilities versus the actual AS severity on the x-axis, where we see that the model outputs nicely correspond to the ground truth severity level of AS. And expanding on this, we now plot the predicted probabilities versus a more fine-grained AS severity, and we find that consistently across cohorts, the probabilities naturally stratify the spectrum of AS severity. Now, this may seem intuitive to you, but remember that the model was only trained to detect severe aortic stenosis, meaning all other categories were bin together. And yet it naturally learns this continuum of AS severity from the imaging from the pixels alone. Now, this work was published in the European Heart Journal in 2023, but this lab's observation was a surprisingly clean one that led us to wonder what else our model was capable of. So if this model could stratify AS severity, could it potentially predict AS progression? Meaning, could its probabilities tell us something about the future risk of developing severe AS? This could have major implications for patient care since detecting and treating AS before it becomes severe is critical to ensuring favorable outcomes. In a follow-up work led by my collaborator Evan Economou at Yale, we sought to answer this question with DASI, or the Digital Aortic Stenosis Severity Index, which is simply the output of the severe AS model I just presented. Using a cohort of patients who underwent longitudinal echo imaging repeated over time over many years, who did not have severe AS at baseline, we essentially evaluate DASI as a potential biomarker for future severe AS. We find that DASI values over zero point 0.2 at the first visit were associated with a five-fold increased risk of later aortic valve replacement, indicating severe AS that required surgery, even when controlling for all the best-known demographic and traditional risk factors. So what this figure shows is that DASI is even associated with the quantitative rate of AS progression, measured by the year-over-year change in aortic valve peak velocity, a key measurement for determining AS severity. Meaning higher values of DASI, this risk index, also corresponded to more rapid progression to severe AS. So not only can this model detect severe AS at the time of imaging, meaning diagnose severe AS as it was trained to, but it also has prognostic value in assessing future risk of AS progression and catching it early. To quickly touch on another follow-up work, we also applied this modeling pipeline to detect rare cardiomyopathies, and critically, we validated the models on point-of-care ultrasound acquisitions from the emergency department. These are often noisier videos from technically limited studies, so successful translation here was a very promising sign for this technology's potential to expand access to lower resource communities that are primarily using portable, even handheld ultrasound devices. And we'll revisit this idea of evaluating our models on limited studies and what that means for the clinical use cases. So returning to our roadmap, we just covered our method to detect aortic stenosis. This model was trained on a data set of parasternal long axis videos for this one important task. And next, I'll present our recent work expanding this goal to fully automated echo interpretation that more accurately reflects clinical practice and needs, where multi-view imaging is used to assess many aspects of cardiovascular health all at once, not just one. I'll stop here to answer some questions, maybe. I don't know if I can see them easily, honestly. Let's see.
Yes, I think we have a few questions in the chat. Um, okay, we can probably start from the latest question. How do you determine the baseline for DASI?
I'm not entirely sure what they mean by that. The baseline label?
I'm assuming it's about the baseline performance. Like, what is it being compared against? Amir, if you're here and you want to elaborate on your question, please go ahead.
Yeah, yeah, I just wanted to know, like, when you're comparing different years, like somebody can start its monitoring, let's say,
Mm.
when they are sick, the other person start their monitoring when they are normal. So how are you comparing these people and their DASI score?
Okay, I think this is a question basically about cohort construction. So the way we designed this study is we found patients who eventually developed severe AS, but during their first visit did not present with severe AS. They either had no or early or mild to moderate. Um, so hopefully that answers your question. It's this cohort by construction has patients who did not initially present with severe AS.
Thank you.
Okay.
Okay, and I think we have other questions about the again your frame. Why choosing frame reordering as the target task here? Are contrastive learning and
Mm.
reordering trained sequentially or together?
Okay, this is about Echo Clear, the first method here.
Yes.
So this was, we basically consider this to be an additional pre-training task to force the model to gain some temporal knowledge. Whereas if you just applied SimClear, this existing contrastive learning method, it's only gonna apply to the still frames. It learns nothing about temporal dynamics, which are needed, we argue, which are needed to perform these downstream tasks successfully. So it's a separate task to imbue some sense of temporal understanding.
And I think we have another question about the same. I didn't catch how EchoClear addresses the challenge of noisy echo videos. So I think somebody is asking about the noise in the data set.
I see. Um, Honestly, this is not something that's specifically addressed. For example, we're not doing any filtering based on noise, which is a common practice. And I think that's actually an asset to our approach, that our model is able to learn from these very noisy acquisitions. I mean, as I mentioned, these are manually acquired by very skilled human experts. Sometimes there's large variability in quality. So we should build models that are capable of learning from these noisy acquisitions, and that's what we aim to do.
Perfect. In the contrastive learning step, did you consider making closer representation for features or metadata from the echo? Um,
Features
I'm
of metadata. Let's see.
I'm not sure who is asking that question, but
I'm gonna guess that means from non-imaging features, like external features. If I'm
uh,
interpreting that question correctly, maybe they're, yes, that's what they meant. Okay.
yes.
Um, yeah, that's a very interesting question and something we've considered maybe doing in follow-up work, like including other auxiliary patient information like their demographics or, you know, lab tests or other types of imaging, could be cardiac MR or ECG. But for this use case, we aim to learn from the echocardiography pixel data alone.
Okay. Thank you very much. I think that's all for the questions. So
Okay.
we can probably move forward.
Sorry, I had one quick question.
Okay.
Feel free to answer this in the end if you think it's better addressed then. What's the role of ensembling? Like, I know that you already showed your basically your pre-training kind of outperforms random initializations as well as the Connect, the other baseline.
Genetic.
So, what's the purpose of actually ensembling them? Do you actually get a diversity of representations by doing different kinds of pre-training? And did you compare about like basically if you just choose different variations of your own method compared to like maybe choosing the other
Yeah.
two? What were your sort of thoughts on
That's a
that?
that's a good question. It was actually sort of inspired by this plot where you see these three different models. They're the same model. Sorry, here. These three different models, sorry, three identical models with three different weight initializations. When fine-tuned on lots of label data, they perform roughly the same downstream. But we know that because of the sort of weight trajectory during training, they started in such different places that their weights are going to be quite different. Basically, how they arrive at the answer will be different. And that's our motivation for choosing them as the members of our ensemble, under the hypothesis that they would provide more diversity than, say, some small tweak, like changing the random seed you start with. So the idea is to pick really diverse members for your ensemble.
Got it. And the fact that in your interpretability, you kind of see that maybe the other one is less
It's more
focused, like does that
diffuse, more
matter?
general.
Okay. So it's a feature, not a bug. Was that the reasoning that you wanted to you have both or
Well, I guess the point I'm trying to get across with this slide is, if you had to choose between these two models that are otherwise identical in all ways, except for their interpretability qualities, however much stock you put into saliency maps, I would choose the bottom one, right? If we
Mhm.
trust the clinician opinion that this is in fact attending to the more important regions and not relying on some shortcut or confounding variable.
Got it. Okay. Thanks.
All right, getting back. So back to our roadmap. Will now present my work on fully automated echo interpretation that more accurately reflects this clinical practice and needs based on multi-view imaging recently published in JAMA. So a complete TTE exam consists of dozens of acquisitions. These are still frames and videos from many different views of the heart, both with and without color Doppler, as well as other forms of Doppler I haven't even mentioned. Unlike modalities such as CT and MRI with standardized acquisition protocols that are perfectly performed by sometimes million-dollar machines, cardiac ultrasound is very operator dependent and requires very skilled technicians to acquire usable diagnostic quality images. Similarly, on the interpretation side, after acquisition, here's what a typical echo report looks like. A cardiologist will synthesize this multi-view imaging information to assess all the dimensions and function of the major chambers and valves of the heart. This comes in the form of quantitative measurements as well as categorical assessments of abnormalities affecting all the chambers, valves, vessels, and more. And for reference, this of course varies, but it takes roughly 30 to 45 minutes to acquire a full TTE study, and depending on the complexity, maybe 5 to 15 minutes for expert reporting. So I have two takeaways I want to impart about this process, which is the current clinical workflow. One, echo interpretation is inherently a multi-view, multitask problem. While prior approaches to AI for echocardiography, including my own that I just presented, are catered to single view, single task settings. Basically, there's a gap between clinical practice and our current AI approaches to echo. And two, echo interpretation is time intensive and costly. Now, 5 to 15 minutes might not sound like much, but when you need to read hundreds or thousands of studies, this quickly adds up. And given the ongoing shortage of sonographers and cardiologists and the increased demand, the projected increasing demand for echo given our aging population, AI-assisted reporting of echoes could help lift this burden by freeing up cardiologists to spend more time caring for patients and even expanding the reach of echo to areas without access to these highly trained experts at all. So with this in mind, our goal was to develop a sort of pan scan for echocardiography, assessing all key labels from all views of the heart in the same way that a cardiologist would. Our model, PanEcho, is trained on multi-view echocardiography, including color Doppler, and extensively validated across time, geography, patient populations, clinical settings, and even equipment. First, we internationally validate the model on complete diagnostic quality echo studies in New England, at 2 sites in California, and an international site in Hungary. What's unique about the studies, we also validate the model on real-world point-of-care ultrasound acquisitions from the emergency department, ensuring that the model generalizes to these limited settings beyond what we would find in major research hospitals with clean data. So to do this, we curate a dataset of over 1 million echo videos from all views using a cohort of nearly 30,000 TTE studies from the Yale New Haven Health System. For each study, with the help of clinical collaborators, we isolate 39 key labels that form the core of a complete echo report. This is not an exhaustive list of all echocardiographic measurements and labels, but rather a sort of minimal core set that one would expect to find in a complete report. This consists of a mixture of 21 continuous measurements and 18 categorical findings, spanning all aspects of cardiovascular health, assessing the size, structure, and function of the chambers, valves, and more. And critically, this also sets up a very challenging multitask learning problem. So our method, PanEcho, is a deep learning model that takes a 16-frame echocardiogram video clip and feeds each individual frame to a 2D image encoder. This is a convolutional neural network, a convnext architecture that extracts spatial patterns from each image and produces an embedding of each frame in a video. These image level embeddings are then modeled as an ordered sequence by a transformer, which then learns time varying patterns over the frames in a video. These representations are then pooled into a single video embedding, which is finally used as input to our task-specific output heads that simultaneously model 39 diagnostic tasks spanning a complete echo report. The model is trained end-to-end on over 1 million grayscale and color Doppler echo videos, directly optimized for all key labels with a multitask loss function that I'll dive into in the next slide. I want to highlight that this is a parameter efficient approach that decouples the spatial and temporal learning and also shares the computation of encoding the echo videos or the feature learning across tasks, only performing the task-specific modeling at the end with these lightweight, fully connected output heads. So specifically a little bit into the process and how we formulate the multitask learning task. A video clip is fed into PanEcho. We receive 39 outputs corresponding to all of our tasks of interest, and then we compute our task-specific loss, which simply for classification task is a unweighted cross-entropy loss Sometimes these tasks are binary in nature, sometimes they're multi-class. We use the appropriate activation function. And then for our regression, these continuous estimation tasks, we use a mean squared error loss. But we use a little heuristic here because many of these continuous labels use such different units and are of different scales, we need to make sure that the losses are on a similar scale when we combine them together. So a heuristic we use is after computing the mean squared error loss, we divide by the mean value of that label observed in the training set. And then finally, all valid losses are then averaged. They're aggregated to form this single multitask objective. And that loss is then is back propagated to the model and used to optimize that model. And I don't show this here, but at test time, the model then integrates multi-view imaging by aggregating predictions from all videos acquired during a study to produce study level predictions for each task. So now onto evaluation. We first validate PanEcho's diagnostic abilities using all available views acquired during complete TTE studies. Here, each row represents a diagnostic classification task with PanEcho's performance on that task measured by AUROC. We see that PanEcho excels at assessing the ventricles of the heart, reaching 0.98 AUC for detecting significant left ventricular or LV systolic dysfunction, 0.94 for significant LV dilation, that's increased size of the left ventricle, among others. The model also accurately assesses the valves with 0.98 AUROC for severe AS, 0.96 AUROC for mitral valve stenosis, and accurate detection of valvular regurgitation, essentially a leaky valve, which requires color Doppler imaging. And across 18 diverse diagnostic tasks, PanEcho achieved a median AUROC of 0.91 in the internal test set. It also maintained its performance upon international validation in the external RV-ENet Plus cohort from Hungary, and finally reached 0.94 median AUROC in external sites from California as well. Now, in addition to these categorical classification tasks, PanEcho also accurately estimates these continuous echo parameters. Here, each row represents an estimation or quantification task, and PanEcho's accuracy is measured by mean absolute error listed on the right here. PanEcho again predicts key measurements of the LV structure and function, like the LV ejection fraction within about 4% on average, and overall accurately estimating a wide array of 21 parameters beyond the left ventricle. And again, since these quantities vary so widely in terms of units, I'm describing overall performance with a normalized mean absolute error. This is simply MAE divided by the mean ground truth measurement. And again, strong performance is maintained in the external RVENet Plus cohort and the EchoNet cohorts from California. And critically, PanEcho performance on each of these tasks is comparable with existing state-of-the-art AI models that are specialized for each task, whereas our approach efficiently models all of them at once. Beyond this, we also evaluated PanEcho's predictive performance in limited imaging settings with two cohorts. First, the abbreviated TTE cohort is a subset of the internal test set where we only use a maximum of 5 videos from the following key views per study. This was meant to simulate a simplified 5-video imaging protocol from diagnostic echo. We also validated the model on real-world point of care scans from the emergency department. Like I mentioned before, these are noisy, simplified studies performed at the bedside, often by non-sonographers, simply to rule out major abnormalities. In these point of care settings, the goal is to rule out gross abnormalities, like I mentioned, so fine-grained measurements are not typically performed, and colored Doppler is typically not available. For this reason, we evaluated PanEcho performance in these settings across 15 tasks that are evaluable by human experts on 2D grayscale echocardiography. And across these 15 tasks, PanEcho maintained 0.91 median AUROC on this abbreviated TTE cohort and 0.85 median AORC on these point of care scans, maintaining strong performance on key findings from these heavily limited acquisitions. Now, beyond performance, we also assess the model's interpretability. In Echo, not all views are equal. Depending on the task at hand, only certain views will capture the structures of interest. So for this reason, it's critical to understand how PanEcho is making its predictions and which views it's relying upon for each task. So to answer this question, we used the predictive performance of PanEcho on a task, given only videos from a single view as a sort of proxy for that view's relevance to the given task. This gives us a view relevance score where 1 represents the most informative view. We discovered that PanEcho naturally identifies which views are most informative for each task in line with standard assessment guidelines. For example, apical four-chamber or A4C was found to be most informative for assessing LV function. And I think most interestingly, colored Doppler videos were by far the most informative for assessing valvular regurgitation, more so than any single 2D view, accurately reflecting clinical knowledge and practice where color Dopplers needed to assess regurgitation. Finally, even though PanEcho was trained on an older population from one region of the US in New England, it can efficiently adapt to novel domains such as a pediatric population. We hypothesize that because of PanEcho's diverse multi-view, multitask training, its knowledge rapidly transfers to this new domain. We find that PanEcho more accurately estimated LV ejection fraction in a pediatric population, more accurately than a randomly initialized model. It also outperformed other transfer learning approaches based on millions of natural images and videos. It even outperformed a state-of-the-art foundation model called EchoClip, pre-trained on over 1 million echocardiograms. And not only was this model more accurate in this setting, it also converged nearly twice as fast, translating to considerable cost savings and more rapid iteration for practitioners who want to use PanEcho to develop models on their own local data. So in summary, PanEcho is an end-to-end solution for echo interpretation that uses multi-view imaging to automatically perform all key diagnosis and quantification tasks. The model demonstrates state-of-the-art performance on both complete and limited studies. It's validated internationally across clinical settings. It naturally identifies which views are most relevant to each task, and it can be used as a foundation model to rapidly adapt to new downstream tasks and settings. So this work was presented at the AHA's annual meeting last November as late-breaking science and was recently published in JAMA in June. Before I wrap up, I want to briefly touch upon some of the clinical implications. We see basically two paths for deploying PanEcho. First, in echocardiography labs, PanEcho could serve as a sort of AI pre-reading step to provide an additional layer of support to expert readers. Now, how exactly this is implemented and what that AI clinician collaboration will look like will be the subject of further study. PanEcho could also provide sort of retrospective audits of large databases of historical echo imaging. This is a task perfectly suited for a deep learning algorithm where hundreds of thousands of studies could be analyzed at scale in a way that, of course, no human could. And the goal of a PanEcho audit would be to flag certain studies for abnormalities that may have been missed the first time around during the initial read and might require follow-up. And second, we believe PanEcho could be used for AI-enabled screening in lower resource communities that do not have access to the expertise or equipment to perform complete TTE exams. PanEcho could quickly rule out abnormalities that might require urgent cardiology referral based on these simple portable acquisitions from cheap devices, especially given that we've seen the model's strong performance on limited studies and on point-of-care ultrasound. Now, what is actually needed to improve this work and translate it to the clinic? I want to leave these open for discussion. So I'll just briefly highlight first, we want to prospectively validate this in a real clinical workflow to see what effect PanEcho would have on the accuracy, speed of interpretation, and ultimately patient care. And second, there are other acquisitions in a full TTE exam that we can include, like still frames, spectral and tissue Doppler, there's strain analysis, and so on. Third, we can improve how we aggregate information across views. We already know that view importance depends on the task of interest, so incorporating this information somehow at inference time, or perhaps allowing the model to naturally learn view importance during training will be necessary. And lastly, we adopt a direct regression approach to our numerical estimation tasks, while the real-world workflow requires manual segmentation or tracing of compartments of the heart. Our approach works very well, as we've shown, but it might not be interpretable to cardiologists who need to be able to trust the model's outputs and ideally even edit them in a way that's native to their workflow. One last thing I want to highlight is PanEcho is fully open source for academic research use. You can access the paper and the model weights and source code with the QR codes here. I want to finally thank my PhD advisor, Atlas Wong at UT Austin, as well as Evan Economou, who co-led the PanEcho study with me, and Rohan Kara, who's the PI of the cardiovascular data science lab at Yale Medicine. These are incredible clinician scientists whom I've been really grateful to work with and be mentored by throughout my entire PhD. With that, thank you for your attention. I'm happy to discuss further, answer any questions here. You can also feel free to reach out afterwards as well. You can reach me in a variety of ways. Thank you.
Thank you, Greg. Thank you for this really interesting talk. Before we move on to the rest of the questions that we see here in the chat, I would like everybody to kind of give a round of applause to our speaker. Awesome. So one of the questions that we have here are the video clips for same patients in EchoClear registered based on anatomy or temporally aligned?
I see. There was no manual registration, either spatially or temporally. The idea, sort of similar to another question that was asked earlier, our philosophy here is to sort of be able to work with the whole breadth of data that you would encounter in the wild without manual intervention or cleaning the data. So no registration was performed.
Okay. The second question is how many views are used in total? What if there are missing views for subjects?
That's a great question.
Reference to, I think, slide number 25, I guess.
Let's get back here. Or maybe, oh, I see. Yeah, that's a great question. So the way the model works is that maybe a better place is earlier. Let's see. Okay, the way the model works is at test time, it will use all available data acquired during a study. So in the case of a limited point of care exam, that can be as few as 3 or 4 videos from just a few views. And in a complete TTE exam where we have high quality data, that can be 50 to 100 videos from all possible views you can imagine. So it varies and is the sort of design philosophy is that the model is view agnostic. It doesn't care what views are encountered. It simply leverages all available data to make the most informed decision possible.
Just a quick follow-up on that. So during inference time, during your point of care, like the POCUS setting,
Mhm.
how many videos do you typically have and how many views do you typically have?
Let's see. Very good question. That's sort of answered in this little pseudo table in the figure here. So this tells you the number of videos per study, the median. Now, in these complete TTE studies, that's roughly 17 up to 20, meeting our criteria. And yeah, in these point of care exams, that's about 6. So it's a very small number.
Oh, okay. So the next question is, does number of specific tasks affect accuracy? Can you train one model for each task? What makes multitask provide? I don't know if that,
Mm.
yeah.
Yeah, I think I understand. That's a good question. So I would say the status quo, the typical approach would be to develop a completely independent model for each task. And we argue the sort of, you know, central hypothesis of our work is that it will be more efficient and scaled to deployment more realistically to model these all at once. Not only, so first, this is a practical consideration. It will be much easier to logistically deploy one universal model rather than trying to handle the logistics of simultaneously hosting, for example, 39 models in parallel. But second, this also more accurately mimics what a cardiologist is doing, right? They're assessing all of the multi-view imaging at once and assessing all of these aspects of cardiovascular health at once. So this is done to be more efficient in keeping deployment in mind and to more closely mimic the real world workflow.
Thank you for that the answer, Greg. But my question was, how is it better to do it like one task, one model, or
I see. There is, this is actually also an interesting theoretical question. There is this concept of negative transfer that argues in multitask learning, sometimes optimizing toward one task may actually hurt you in other tasks. It's a very challenging problem where some of these tasks are actually explicitly at odds, for example. So the answer is probably, in principle, it would be more optimal to develop these specialized models for each one, but we argue that that's not tenable for deployment and doesn't mirror the clinical workflow.
Okay, thank you. So
Yeah,
the
there's a
next
trade-off
question,
there. That's
yeah,
a great question.
yeah,
Sorry.
yeah. So the next question is, how do you train or balance the temporal transformer given 39 tasks in total? Just an average of 1 by 39 weighted sum, or you find some main tasks contributing more?
Hmm. Do they mean in the learning process, like in optimizing the model?
Yes,
Veji, if you
yes.
want to jump in and say what you were asking.
Can you hear me now?
Yeah.
Hmm.
Okay, yes. I just wondering like you have multiple task, right? And the main the part one, part two, the encoder and transformer are the same. You just train the last the free connection layer. Then how do you train the transformer if you have so many tasks? I I mean, if you will choose some task like weighted more
I see.
or just do the average.
I see. Yeah. So the way we handle this during training is simply averaging the task-specific losses.
Okay,
And right, however those are balanced during training is however they're balanced, right?
okay. Thank you.
Okay.
But yeah, you could imagine an approach where you apply some weights externally based on some prior domain knowledge, but we prefer to just learn from the data itself.
Okay. Yes.
Okay. So the next question is, have you tried a true 3D pre-training rather than 2D feature extraction? And then
Mm.
extraction and temporal concatenation.
That's also a great question. This also kind of speaks to the design philosophy, why we chose this architecture. So certainly in the other two works I presented on the single view self-supervised learning and EchoClear, and also on the severe AS detection work, we actually did do spatiotemporal learning, right? These are 3D convolutional models. But for PanEcho, we decided to sort of decouple it and do this 2+1D learning, sort of like you're alluding to. And the reason we chose to do that is for flexibility downstream. It's not necessarily that I think a 2+1D approach is always superior to a 3D approach, but the idea is it lets people use our model as flexibly as they want. So if they just want to take the 2D encoder for some downstream task of theirs that only leverages still 2D ultrasound images, then they can take just the 2D encoder and fine tune that. And similarly, if they are doing some echo interpretation task or measurement task based on video clips, they can take the entire model or the entire encoder. Whereas if we had a 3D model that's doing these 3D convolutions or some other operation, it's a bit more difficult to adapt it to a 2D task downstream, if that makes sense. That's a
Yeah.
very good question.
Okay. So we have two more questions. How do you account for the beating of the heart or respiration compensation?
The honest answer is we don't. We this is also perhaps just my philosophy on how to learn from data like this and how to design models is to choose a simple, scalable approach and have those patterns be learned at scale. So when the model is encountering so many different examples, it's a million different videos from 30,000 studies, it's going to capture almost all of the variation you would see in routine clinical practice. So it will be exposed to all of the different phenotypes you would be able to capture and all of the different variations in scanner and acquisition protocol that vary by who's acquiring it, vary by where it's being acquired. So I hope that answers your question.
Perfectly. Uh, One more question. Did you try using a meta classifier rather than simply averaging the predictions from all the views?
A meta classifier. I might need clarification on that. Does that
I,
mean?
I can explain my question
Sure.
there. So essentially, rather than aggregating them equally, like you said, by averaging the predictions from each of the views for one of the tasks,
Yeah.
did you try using like a trained like logistic regression using those predictions? Because you were talking about maybe finding a way for the model to learn how to properly weight the views for a specific task, right? So like you said, let's say
Yeah.
you want to look into cardiomyopathies, right? I know the A4C view is going to be great for any like left ventricular diseases, whereas like you said, aortic stenosis would be great with PLAX, maybe some sort of I don't know if you tried using a some sort of meta classifier that it could
Yeah.
learn the weights of the predictions for each task.
Great question. So that's sort of exactly what I'm hitting upon with
Right,
this third bullet point here. So for this approach, for PanEcho as it's currently available, we do you could argue a sort of naive approach, right? Uh, we're giving effectively equal weight to each video, averaging the outputs, even though we know that's not uh,
right,
necessarily what would be happening in clinical practice. So I have run experiments on this using like a frozen PanEcho model and then training a simple transformer layer, various different approaches to try to dynamically weight videos and have the
right.
model learn that. Honestly, the initial experiments show pretty similar performance to naive averaging, but I absolutely believe that there is room for improvement here, not only in terms of performance being left on the table, but just in mirroring what we know to be clinically true, that only certain views should
Yeah,
even be relevant to certain
yeah,
tasks.
absolutely. Yeah,
That's
just trying to
important future
yeah,
work.
just mimicking the workflow. Yeah,
Yeah.
absolutely. Thank you.
Uh, but I see we still have a few questions, but I guess for the interest of time, uh, maybe we can take one more. Mehul, do you want to go?
Yeah, good. Thank you. So this is really nice to Greg. It's really nice to see your architecture of like a 2D CNN and a transformer. About 6 years ago at RSNA, there was everybody was trying to do 3D classification of intracranial hemorrhage in CT images, and
Mm,
a lot of us were trying this 3D CNN, but the top approaches all had an 2D image encoder, and at that time LSTM, right?
yeah.
2D, and it was incredible, like how much better that approach did compared to the 3D CNN approach. So it's nice to see that you have that. Yeah, you have the next generation of that, right, with the transform.
Mm,
Um,
mm.
one like that's just a comment, a boring question. Like before your images go into the image encoder, um, did you have to do like normalization of these ultrasound images? Because imagine like all these different manufacturers, how did you make it robust?
That's a great question. So yeah, that's a great point. You get a ton of variability depending on the scanner of choice. There are also vendor settings that can be modified. Like sometimes these grayscale B mode acquisitions will appear. I've seen them appear in sort of a sepia tone. People can modify the settings, based on reader preference.
Mm,
And it's also complicated by the fact that we're sort of jointly training on these grayscale acquisitions and the color Doppler, which has the red blue.
right.
So the simplest approach we take is we encode every video as, I guess, depending on how you count dimensions, 4 or 5 dimensions, um, as RGB.
Okay.
And we normalize with the standard ImageNet means and standard deviations across the channels because that's how the 2D encoder was pre-trained.
Okay, thank you.
I'm really sorry, Winston, Anand, and one, you can ask your questions to Greg directly, or
Yeah,
you
please
can
feel
get
free
in.
to reach out
Yeah,
also.
yeah, and you can get, or you can get in touch with us, and we can connect you to
Yeah,
Greg.
yeah,
Yes.
I will send an email to you to follow up. Thank you.
Yeah,
Great.
yeah. With that, before we sign off, we would like our audience to kind of give another round of applause for this really interesting talk. Uh, with that, maybe we can end the session. Thank you so much, Greg, for joining us today.
All right, thank you all.